Welcome to the 12.5 video, everybody. So we're kind of beginning the last, two sections of chapter 12, and these are all going to be about kind of drawing surfaces and lines and planes in R3. And so we're going to start out with the most basic things, lines and planes, and then in 12.6 we're going to draw some more complicated things. So let's learn how to draw. Let's start with lines. How do we draw lines in R3? Okay, so obviously their lines still exist on R3, but we got to think about how to write them. So an example of the problem we have is like this equation, x plus y equals 7. In R2, that's clearly the equation of a line, right? We could rearrange this into point slope form. Maybe it would be more familiar then, right? Okay, that's a line with slope -1, y-intercept 7. Okay, but I think we did this. This was one of the examples in my previous videos. This exact equation. That this equation, when we see it in R3, is not the equation of a line. It's the equation of a plane. Okay. So yeah, if we look at the xy plane, we get this solid blue line here, which is just a line. But then for all the other values, we have similar lines, and then those lines kind of form a plane. So this is the equation of a plane in R3, not a line. And we'll see how to draw planes a bit more methodically as well. But let's stick with lines for now. So this kind of raises the question, how do we write the equation of a line in R3? When we have a line like this solid green line, okay, and I've kind of drawn some angles here to kind of indicate its orientation in the 3D space, okay. So this is the line, and then these are kind of the angles it forms with the axes. Hopefully that makes sense. How do we write the equation of something like that? Now, we can use the same kind of principles we used in R2 to draw to write an equation of this line. So think about how we did it in R2, and in particular, there were several ways to write equations of a line in R2, right? We had slope-intercept form, the so-called standard form, but let's think about the point-slope form, okay? So if you think back to the point-slope form in R2, what did we need for point-slope form? We needed to know one point on the line and the slope of the line, okay? Don't worry about the exact, mechanics of point-slope form, but basically how it worked is, we knew a point on the line and we knew the slope. There's a lot of lines through that point, but if we knew the slope, okay, we knew the exact line, right? We're going to use a similar concept for writing equations of lines in R3. So let's start thinking about R3, and let's assume we know one point on the line. So and remember, we can think of that point as a vector, really. So let's say, and my notation's a bit garbled here. Let's say we have and this is one of my issues with the textbook, is that they make a bigger deal about the difference between vectors and points than I think is necessary. So let's say we have the point P 4, 1, 0 on the line. Okay, so this point is on the line. Well, that means, we can think of that point as a vector from the origin to that point P, right? Which we could just abbreviate as the vector RO. Okay. So the end point of that vector is on the line. Okay, that's the same idea as that point being on the line, right? And let's also assume we know a vector parallel to our line, okay? So this, the endpoint of this vector is on the line, and then this vector is parallel to our line. Okay, so let's kind of draw what we're talking about here. Okay, so let's see, we're saying the point 410 is on the line, so that'd be something like, that's kind of what I've drawn here, okay, that point there. And then we know this vector, -514, is parallel to my line. And I've kind of drawn it off to the side. Okay, 510, okay, so maybe if the base of this vector was at the origin, okay, then its tip would be at the point 510, right? But remember, it doesn't matter where this vector is in space, as long as it moves, you know, -5 units in the x direction, -1 unit in the y direction, 4 units in the z direction. Whether it starts here or here or here, it's all the same vector, right? So imagine that vector's parallel to our line. And it might be helpful to think about it having its base right on top of our point, okay? So if that's the case, that vector is going to be right along our line, right? So let's put that there. So we see that the vector RO, R sub 0, plus V is also on the line, right? So the vector R sub 0 would be like this vector, and then we're adding the blue vector to it, and we get to, let's say, this red point. Okay, so that's on the line. And really, I can pick any point on the line, let's say this. And if I add, I can add a scalar multiple of my vector v, and I'll get to that point, right? So what I'm saying is if that blue vector was a little bit bigger, I could add it to my yellow vector and get to that point there. Oops. Right? And I can do that with any point on the line. And that's what I've said here. If I scale the vector, and that should be v. If I scale v up or down by multiplying it by some scalar, let's call it t, then we can get all points on the line, or any point on the line. So let's say r is some arbitrary vector whose endpoint is on the line, or I can think about it as a point on the line. Then I can always write this point on the line, this vector with endpoint on the line, as r0, that kind of known point, and then a multiple of my parallel vector. Okay, so this is a lot like point slope. I know a point on the line, and I can think of this vector as kind of like a slope. Then any other point can be written as a combination of those. Now this thing here, okay, this equation represents the line. Like these are all my possible vectors with endpoints on the line, or I could think of them as all my possible points on the line, and I can write them all as a combination of that known point and a multiple of that parallel vector. Okay. So since this is a equation of vectors, right? So let's see what we got here. We got a vector here, a vector here, a vector here, and then this is, you know, just multiplying by my vector. This is a vector equation. And so we would call this the vector equation of the line. And t, which is just a number, is our parameter. It's just a parameter in the equation. Now let's talk about t and v. And actually, before we talk about t, let's talk about this vector v. Okay, So we said what, this blue vector was parallel to our line, right? Okay. And we called this vector v, but there's actually a lot of vectors parallel to our line. You know, this vector v is parallel to our line. This vector w, which is a bit longer, is parallel to our line. This vector pointing in the other direction, let's call it, you know, s, that's also parallel to our line. So this v, there's not one vector that's parallel to our line, so there's maybe a lot of possible choices for v. And then what are our values for t? Well, that's kind of arbitrary. We could think about this known point on our line as we could think about that as a starting point. Okay, so at time 0, or not, you know, I say t, I said time. You know, I often think about t as time, but you know, you don't have to think of that. That's a convenient idea to use a lot of times. So we can think about t being 0 at this point on the line. Okay, remember this is like r0. Okay, we're calling that vector r0, and then I'm adding, let's see, we're saying r, any vector on the line can be written like this. So maybe for like t, if my vector v looks like that, maybe at time 1, or t1, t equals 1, where would I be? Okay, so if that's my vector v, at t equals 1, I would be at the point RO plus v, which would be where? Just like right there, right? So maybe at t1, I'm here. And then at t2, I'd be a bit further along, and t3. So I see as t is increasing, I'm moving this way. But that's not really important. You know, if I had used a different vector as my parallel vector, you know, I'd be at different points for different values of t. What's important is that there's, you know, if I want to get to this point, there's some value of t that I'll eventually be at that point, and so on back here. And I can go on for infinity in that direction, keep getting points on my line. So in this respect, we see that t takes values between negative infinity and positive infinity. Okay. So that's my range for t. If I let t vary between these infinities, I'm eventually going to get every point on the line, right? Going this way and that way. And it doesn't matter what my parallel vector is, as long as, you know, it is in fact parallel to my line. Okay. We could also, so this is, we've shown the vector equation of the line, and maybe we should do an example real quick. So a quick, easy example. Find the vector equation of a line passing through the point 1, 0, negative 7, and parallel to the vector 3, 5, 6. Okay. Now, there's a couple ways I could write this. I could say, all right, let's let r0 equal the vector, what, origin, if this is p, that, which is equal to that. I could write that r0 like that. And then I could say, all right, let's let this equal v. Then the equation of the line passing through r sub 0 and parallel to v would just be r equals r0 plus tv. And if I wanted to keep it, you know, written by components, I could say, well, this xyz, this general point, or this general vector xyz is going to be equal to the point on my line plus t times 3, 5, 6. So really not too bad. We'll see some slightly more complicated examples in a bit. But writing it out like this kind of is a nice segue into a different way to write these equations of lines in R3. So think about these components of these vectors, which we've just written out. And let's kind of do it in the general case for now. So we said, okay, R, my kind of general point on my line, is going to be just x, the vector x, y, z. Let R sub 0, that point I know is on the line, or that vector whose endpoint is on the line. Let's call that x sub 0, y sub 0, z sub 0. And then let's say I know this vector that's parallel to my line. Okay, let's say I know its components are a, b, and c. Okay. Then the vector equation is just this, right? This is the same thing as R equals what? R0 plus TV. Okay. But we can condense the right side a bit. Okay, we can write that right side as a single vector by bringing everything inside one set of what would you call those? Pointy parentheses. I'm not sure. I guess vector. I don't know. I'll have to look up what those are called. I don't. In the typesetting program I use, they're just called L angle and R angle. So I don't know what they would be called in normal English. Let's call them pointy braces for now. So we can write this right-hand side as a single vector inside a single set of pointy braces. Okay. And this is just using our basic properties of vectors. Okay. So the component here in that first slot would be x sub 0 plus t times a, then y sub 0 plus t times b, z sub 0 plus t times c. Okay. Now, remember that two vectors, let's say vector a and vector b, these vectors are only going to be equal if all their components are equal. Okay. So when I have this left side is equal to this right side, what I'm saying is that x equals x sub 0 plus ta, y equals y sub 0 plus tb, and z equals z sub 0 plus tc. And now notice these equations, they don't have any vectors in them, right? These are all just numbers, okay? Those are all numbers. And then we have this parameter t here. And so we call these equations the parametric equations of the line. Now, we might write them out just as a list like this, or we might write them in parentheses as so. So parentheses x, y, z equals parentheses x sub 0 plus at, and so on. Now notice these are the rounded parentheses. These aren't vectors. These are it's just like a list of equations, basically. Okay. Now apparently these numbers a, b, and c, which we got from our normal vector, or excuse me, our parallel vector. I'm getting ahead of myself right now. These numbers a, b, and c, which came from our parallel vector, are apparently called the direction numbers. This is, terminology I didn't remember or wasn't familiar with, but they're apparently called the direction numbers. So if you want to remember that, great. I don't think it's a huge deal. So that's the parametric equation of the line. So let's see an example real quick. Let's try and write a line using parametric equations. Okay, so this is the example I just cooked up. Find the parametric equations of the line passing through the point -9, 13, 4, and parallel to this vector 4, 6, 1. Okay, so let's try that. I know that x is going to be equal to, just from my parametric equations, x is going to be equal to x sub 0 plus a times t, or t times a if you prefer. Okay, so what's my x0? Well, that'd be -9. And what's my t? Well, t is just a parameter, so I'm going to leave it like it is. And what's my a? At 4. Okay, so really what I have is x equals -9 plus 4 t times 4. And then y is going to be equal to 13 plus t times 6. And then z is equal to 4 plus t times 1. Now I've got this list of 3 equations, my parametric equations, and again, I could write them in this parentheses notation. Moving on. Now, remember that when I'm writing the equation of a line, when I'm trying to find the equation of a line in R2, even when I was trying to use the point slope form, sometimes we weren't given the slope, right? Sometimes we were told 2 points on the line. So what did we do? We solved for the slope, and then we plugged that slope into our, we picked one of the points and used the slope we found to write the equation of the line in point slope form. And we can do a similar thing in R3. Okay, so maybe we're not going to be given a vector parallel to our line. Okay, so maybe we're going to be given 2 points on the line, but no parallel vector. The first thing we have to do is find a parallel vector. Okay, so a picture of the what I'm talking about is maybe we want to find the equation of this green line, and we're told the points A and B are on the line. Okay, how can I need to find a parallel vector somehow. Well, if I can find the vector that goes from A to B, that's going to be parallel to my line, right? Okay, so let's remember how we find a vector between 2 points. That vector is going to be just the components of B minus components of A. I could also, so that would be the vector that goes from A to B, okay? So that would be so we could say, okay, V is the what? Like V1 minus A1, B2 minus A2, B3 minus A3, okay? That'd be the vector that goes from A to B. We could also just as easily use the vector going in the opposite direction. Let's call this one V, let's call this one W. W could be what? A1 minus B1, A2 minus B2, A3 minus B3. Either one would work for a parallel vector, okay? So I have my parallel vector, and now how can I write the equation of my line? Let's say we're using the vector equation of the line. So let's say I want to write R equals R0 plus T V, where V is parallel. Okay. Which point would I use for my R sub 0? Well, I could use either one. Okay, even if I use the vector going from A to B, I could use either A or B as my point, R0. Okay. And if you don't believe me, write both equations of the line using either one, and you'll see that okay, our location for different values of t might be a little different, but we'll still be on the line. Okay. What I mean by that is, let's say we could write R equals, I'll just do this in kind of a very symbolic way. Let's say we did 0 to a, or the origin to a, as our vector RO. Okay, so this vector. Okay, so maybe at t equal to 0, we'd be located here. And then at t equals to 1, okay, we move this way by vector v, okay, and then at t equals 1, we'd be there, right? Okay, so we're on the line. That's the equation of the line. On the other hand, I could also use r equals 0 to b, or origin to b, as my starting vector. Okay, and I'm using the same parallel vector. So at t equals 0, I'd be here at b. And then at t equals 1, I'd be up here somewhere, but I'd still be on the line. And maybe for negative values, I'd be down here, right? Okay, so we see that there's a lot of ways to write these equations of these lines. So to kind of drive that home, here's 4 different ways to write the equation of the same line. We could have said r equals origin to a plus t times ab, or this, or this, or this. Now, all these are just kind of symbolic, right? OA means the vector starting at the origin going to point A. AB means the vector starting at A and going to B. Okay. So if we wanted to, plug in some numbers, we would just find the components of these vectors and plug them into our equation. So again, let's try an example. Let's find the equation of a line between 2 points. So let's find the equation of the line passing through 4, -1, 16, and 0, 3, -2. Okay. So first thing I need to do is find a parallel vector. Okay. So let's call this A and this B. Okay. So my vector, my parallel vector, I could use either AB or BA. Let's use AB. Okay. What is this vector? What are the components of this vector? Okay, it'd be 0 minus 4, so -4. 3 minus -1, so +4. -2 minus 16, so -18. Okay, so I got my parallel vector. Okay. Now, how do I write my line? Okay, I know r equals r0 plus t times v, where v is parallel. Okay, so what should I use as my RO, my r sub 0? Well, I could use either one of these, okay? Just the vector, not the point. Okay. So let's use b. We could use b. So 0, 3, -2. I'm going to use that as my r sub 0. And then I'm adding t plus my vector, my parallel vector, which is -4, 4, -18. And that's going to be equal to my r, which I could also write as x, y. Okay. So when you're writing these out on the test, you might be asking, okay, how should I write my answer? Okay. I'll put it like this. If you list out like your vectors, like if you say, all right, v is equal to this. And r sub 0 is equal to 4, -1, 16. Then when you write your equation, it would be acceptable to write r equals RO plus TV. Okay, that could be you could use that as your final answer, box that up. But you still need to have, you still need to have written the vector by components somewhere. Or if you prefer, if you don't want to do that, you could just write it like this: x, y, z equals, the vector you're using, in this case. All right, so in this one we used A. In this case, I'm using B. Okay, you could just you write your equation out by components. So either one of these are acceptable, but if you write it like this, you need to say what each of these vectors is somewhere. And in fact, you should probably also just go ahead and say, we got those two vectors, you should probably also say R is equal to X, Y. The textbook goes over something called symmetric equations, which are yet another way to write equations of the line. I'm not going to bother with them. Honestly, it's something, if I've seen it, I don't remember it. It's not extremely complicated. You guys can look at the textbook yourselves and piece it together. It's fairly straightforward. But I wouldn't say, at least in my experience, it's very common. I will say that the branch of math I'm working in, not a ton of this is kind of all geometrical stuff, so not a ton of geometry in what I'm doing, probability. So maybe in fields like physics and engineering, where these kind of spatial relations are really important, maybe they work with these types of equations more. But I don't think it's necessary, and the homework doesn't seem to use it as well. So it looks like we don't need to go over it. Okay. Now let's talk about some slightly more complicated examples with lines. Let's try and find, let's say we have a line and a plane. How can we find where the line intersects the plane? Okay. So an example of that type of question would be like, okay, let's say we have the line with this equation here. At what point does the line intersect the XY plane? Okay, how can we solve for that? Well, and this kind of works for, in general, any type of plane, but in particular, these coordinate planes where we have like the XY plane, the YZ plane, the XZ plane, etc. The first step would be determine the equation of your plane. Okay, so what's the equation of the XY plane? Well, you could think, okay, what letter is missing from here? Z. So Z equals 0 is the equation of that plane. Okay. Now, what you're going to do is you're going to set your parametric equation. Remember, this is the vector equation. We could also do the parametric equation. We could set the parametric equation for this component equal to 0. Okay. What does that mean? Okay, so remember that this line, okay, this is the vector equation. It also has those parametric equations, right? Like x equals what? 7 plus t times 4 and so on. Okay, and then z. Z is the one we're interested in here. Z equals 9 minus t times 3, right? Because this is negative 3. Okay. And on the other hand, we know the equation of this plane is z equals 0. So let's set these two equations equal to each other. Okay. So I have, this is my parametric equation, and then my equation of the plane tells me, okay, the z coordinate is going to be equal to 0 in that plane. So what I do is I just say, okay, 0 equals 9 minus 3t, which is what I've written here. And then I solve for t. So t equals 3. Okay. So the t value where that line intersects the plane is 3. Now I'm going to take this t value and plug it into the equation of my line, which was what? I could plug it into this or into my parametric equations. So when I plug t into this, I should get a point on the line, and that point is going to be where the line hits the plane, okay, which in this case is 19, 5, 0. Or if I want to, write it as a point, 19, 5, 0. A quick, I keep talking about this difference between points and vectors. And this is something I'm doing because that's the way your textbook presents it. But really, I think about vectors and points as being the exact same thing, okay? So when you go a bit farther in math, you talk, if this is R3, okay, this is the space R3, we start calling it a vector space, which means it's just a space made up of a bunch of vectors. So when I think about this element of R3, this point, well, okay, that's just a vector in R3. Okay, so I don't see any difference between vectors and points. So I use the terms kind of interchangeably. So really, any point we could think of as a vector. If I'm looking in R2, this point here, well, that's a vector. That's also a vector with its base at the origin, right? So in that way, I think of all points as vectors and all vectors as points. Just a little note. Okay. Moving on in our discussion of lines and planes in R3. We've seen how to write lines now. What if I don't want to write an entire line? What if I want to write a line segment or array? So remember, array is like a line that goes off to infinity in one direction but stops in the other direction. Okay. So let's start with line segments. What if I just want to write that line segment from A to B? How can I write an equation of that line segment? The process is going to be, pretty much the exact same as writing the equation of a line. Imagine this was a line that kept going, okay, in both directions. Okay, so we know 2 points on the line. How would you write that equation? First, you find that parallel vector, and we could use AB, right? So first you find AB. And then you pick a starting point. You pick either A or, origin to A if you want to think about it that way. Or you pick origin to B as your R sub 0, right? And then you write, okay, R is going to be RO plus TV. Okay. So this is your parallel vector, and this is kind of your starting point or starting vector. And then that gives you your equation of the line, right? The only difference is in your t values. So remember, for a line, your t's were ranging between negative infinity and infinity, right? Because if it was a line, the line goes on forever, so eventually we're going to need infinitely large t values and infinitely negative t values and so on. But if we're writing a line segment, we use this same exact equation, okay? But instead of letting my t go from negative infinity to positive infinity, I just let my t go from 0 to 1. And to see how that works, try it. Try plugging in some values for t. Okay, so if you want to pause and try that for a second, that's fine. Make up your own equation. Let's say, a is equal to, make up your own values of a and b and try it. But what you'll see is, okay, if we're using this equation, and it doesn't matter what the points are, when you plug in 0 for t, where are you going to be? Well, if you plug in 0 for t, that term's going to cancel out, right? And you'll just be at the vector r, which is the origin to a. So you'll be at a. And then if you plug in 1 for t, where are you going to be? Well, when you plug in 1 for t, you're at r equals origin to a plus the vector a to b, right? So you're at this vector plus this vector, so you would be at the point B, okay? And then, as you might imagine, for any value between 0 and 1, you're going to be somewhere on that line. Okay. So fairly straightforward. And what about array? What about something that starts at a point and goes off infinitely in one direction? Okay. Well, in that case, and I'll kind of let you puzzle over this yourselves, I'm not sure it's in the book, but you would let your t range from 0 to infinity. So let's say, you use A as your starting point, right? And then, okay, maybe we knew the point B as well, okay, on that line. We would say, okay, R equals OA plus TAB for t between 0 and infinity. So at t equals 0, we'd be there. At t equals 1, we'd be there. And then as t increases, we're moving farther and farther down the line. Okay, but if t can't be negative, we're never going to be down there. So let's see if we an example. I think we're good without an example for those. Let's move on to planes. So we've seen some very simple planes in R3, right? Just in this video, we've dealt with these two equations here, z equals 0. That's going to be the xy plane, right? So at z equals 0, a quick and ugly R3. Okay, that's our R3. Z equals 0 would be that horizontal plane, right? And then we drew x plus y equals 7 earlier. You can rewind the video to check that out. So these were kind of easy examples, but how can I write the equation of a plane that's a lot more general? Okay, so I'll kind of try and draw some stuff to kind of give you an idea of the orientation. So maybe if we drew a line, from the origin to the plane, okay. Okay, so it's kind of tilted there. The plane doesn't even intersect the origin. So how can we write the equation of that plane? Let's start developing this theory. Okay, so a plane, even if it's inside R3, the plane itself is still just a two-dimensional object, right? So we have this two-dimensional object in R3. Okay, so this green plane makes up 2 dimensions. I can always draw. There's always like a third. We can always find that third dimension. I can always draw a vector coming out of the plane, okay, in some other direction, okay? So you could think of this as like, okay, this plane is 2D, and then, I'm in 3D space, so I can always find that third dimension, okay? This vector that goes off in this third dimension, okay, I could draw this vector at a right angle to the plane. And let's draw it in a different color. Maybe I could draw these vectors at a lot of different angles to the plane, like, 110 degrees, 40 degrees, etc. But let's always think about these planes going through, like, piercing through the plane. Let's always think about them as like piercing at a 90-degree angle, okay? This type of vector that pierces the plane at a 90-degree angle, we call that a normal vector. So we can always draw these vectors. And what do I mean by, when it pierces at a 90-degree angle, that means the vector is orthogonal to or perpendicular to the plane. Okay. And as we said, such a vector is called a normal vector, and the standard notation is to write it as vector n. Now, when I say this normal vector is orthogonal to the plane, and I've misspelled orthogonal here, I left out some letters. Okay. When we say this vector n is orthogonal to the plane, what I mean is like if r is any vector in the plane, then my normal vector n is going to be orthogonal to that vector. Okay, so think about this. This blue vector here, let's call that, and that's our n. Okay, that's orthogonal to the plane, right? And then this green vector here, let's call that r. Okay, this is just some vector in the plane. Okay, so the plane goes on forever this way, and it goes on forever that way, and a bunch of other directions. But this vector here with starting point here, ending point here, that's inside the plane. Okay. All right, so if n is orthogonal to the plane, it has to be orthogonal to that vector in particular. Okay. And remember, when two vectors are orthogonal, their dot product is 0. Okay. Now I've just spit a bunch of facts at you. How can we use this, these facts to write the equation of a plane? Well, it turns out that if x sub 0, y sub 0, z sub 0 is a point in the plane, and n is the normal vector with components a, b, and c, okay, we can form a vector orthogonal to n from any arbitrary point in the plane and this point. Okay. I've stated that poorly. Let me regroup here for a second, and I'll try my hand at that again. Okay. So let's try this explanation again. Okay. So these are the two things we need to write the equation of a plane. Okay. We need some point in the plane that we know. So let's say this point is in the plane x sub 0, y sub 0, z sub 0. And then we know this vector is orthogonal to the plane. It's the normal vector. It has components a, b, and c. Now let's think about the other points in the plane. Okay, and this would be a good place to insert another picture. So let's copy that from here. What do the points in the plane look like? Like I want to find the points x, y, z that are in the plane. Okay. So let's say I know, let's make this, let's start way from the beginning. Say, okay. So let's say I know this yellow dot is on my plane, and I know this blue vector is normal to my plane. Okay, and maybe this blue blue vector, you know, it's over here. It doesn't matter. We can always move it to here, right? With its base at the yellow point. Okay. Now, how can I write the points x, y, z in the plane? Okay. So like this point here. Okay. What do I know about this point? Well, if I draw a vector from my yellow point that I know to this point, which we'll just write as x, y, z for now, that's a vector in the plane. And since that's a vector in the plane, it's going to be orthogonal to this blue vector, right? Like this is going to be a 90-degree angle right there. So the dot product of these two vectors is going to be 0. In other words, all right, so how can I write this vector, this white vector here? Okay, if this is my point x sub 0, y sub 0, z sub 0, that vector is x minus x0, y minus y0, z minus 0, z0. And it is going to be orthogonal to this vector here, which is a, b, c. So I know that this equation, this dot product, is going to be 0. And the rest, this really is the equation of my plane. The rest is just kind of rearranging it, okay? Remember what the dot product is. It's this times this, plus this times this, plus this times this, which is just what I've written here, okay? And this is exactly the equation of my plane. And we call this the scalar equation of the plane, because again, I've split it up so there's no vectors here, right? It's just numbers, just scalars. So this is the scalar equation of my plane. Quick note that, okay, this is usually how it's written, but maybe we distribute these multiplications and rewrite it in this form, where I have a times x plus b times y plus c times z. And then I collect all the other numbers and combine them into a single constant d. And I say, okay, blah, blah, blah plus d equals 0. Or maybe I bring that constant over to this side, and it would technically be, negative d over here, but I just wrote it as f, okay? Don't think that, okay, because it's negative d, there doesn't have to be a negative sign over there, right? That number could be like 5. Okay. So these are all 3 equations of a plane. Okay. And again, these are called scalar equations of the plane. Now, there's a kind of easy way to recognize the equations of a plane. And I've kind of started a thought here saying that, okay, if the equation is linear in x, y, and z, it's the equation of the plane. What does that mean? Okay, if I have x, y, and z in my equation, okay, if I know I'm in R3 and I have x, y, and z in my equation, and they're just multiplied by constants, okay, it's the equation of the plane. Okay, so ax plus by plus cz, okay, these variables are only multiplied by constants. If we have that, it's definitely going to be the equation of a plane. And maybe that one of those constants or some of those constants are 0. So if b is 0, for instance, then that whole term is going to disappear, right? But even if it's not written, we can imagine it's there as like 0 times y. Okay, so this is still the equation of a plane. We're multiplying y times a constant. Okay. Now, where it stops being the equation of a plane is if we do anything fancier to x, y, and z. So if I had like ax squared plus by plus cz. Okay, this is no longer the equation of a plane because I haven't multiplied x by just a constant. I've done other stuff to it. I've squared it. Okay, so this is not the equation of a plane. Just a quick note there. Now, we wrote equations of lines in, well, actually, before we move on, let's do an example real quick of writing the equation of a plane. So let's try this real quick. Let's write the scalar equation of the plane that contains the point 1, 1, negative 9, and has a normal vector 4, 6, 4. Okay. Well, let's see. I know what's the equation of my plane going to be. A x minus x0 plus b y minus y0 plus c z minus z sub 0 equals 0. Okay, what's my a, b, and c? Those are 4, 6, and 4. Okay. Okay. And then I leave my x, y, and z as they are. And then I subtract the point I know. Okay. So I subtract those components. Now, since it's negative 9 here, that becomes a plus. And that's the equation of my plane. Now, I could have, like I said, distributed this. Okay. So this would be acceptable, and if I distributed everything, I'll get this, and I could combine all of these into a single constant. So that would be what, minus plus 26 equals 0. Okay, so this would also be acceptable, and so would this. Now, just like with lines, we wrote them using vector notation and scalar notation, right? So far we've seen scalar notation for the plane. Let's see how we can write it using vector notation. Okay. So let's say r sub 0 is the vector with the endpoint on the plane. So that's the point we know is on the plane. Okay. So again, let's use yellow for that. Okay. So maybe r sub 0 would be that vector, right? Whose endpoint is on the plane. Okay. So, and then this green vector is our vector r. That's also got an end. Well, actually, no, it's not going to be that green vector. R would be this vector here. So this is just some other vector with an endpoint on the plane. Okay. Well, r minus r sub 0, what is that? Would be the green vector. That vector is going to be inside the plane. So this is r minus r0. Okay, that point is inside the plane, so we expect it to be orthogonal to that normal vector n. Okay, so we expect r minus r0 to be orthogonal to n, so their dot product should be 0. So I should have this equation satisfied. So we call that the vector equation of the plane. Okay. So let's see another example, just real quick. Let's say r sub 0 is the vector 1, 4, 6, and my normal vector is 0, 0, 3. Okay, then I know, let's see, the vector equation of the plane is going to be n r minus r sub 0 equals 0. Okay, as long as I've, and let's see, I could write my r as x, y, z. Okay, so as long as I've written out these three, okay, my final answer could be written like this. Okay, if I don't want to write out these 4 equations, I could write out the single vector equation. I could also write this. And then again, I could combine these into one vector as well. So these would both be, well, these two and this block would all be acceptable answers for finding a vector equation of the plane. Okay. Now let's look at some special cases. What if I'm not given a normal vector to the plane? How do I cope with that? So again, this is kind of like in the line examples when we were given 2 points on the line, but we weren't given a parallel vector. Let's say we're not given a normal vector to the plane, but we are given 3 points in the plane. Okay. What we do is we make a normal vector. And we're going to use a tool from the previous section the cross product. Okay. So let's say I want to find, and let's just do an example to show how it works. It's pretty straightforward as long as you're comfortable with the cross product. Let's say we have a problem where we're told to find the equation of the plane containing these 3 points, P, Q, and R. Okay. P is 1, 2, 1, Q is 0, 0, 1, R is negative 1, 0, 3. Okay. Well, what we're going to do, and it might help to see a picture real quick. Did I draw a picture? No. Okay, so let's draw a picture real quick. It's not going to be super detailed. Let's say I have a plane. Okay, so let's say I have this plane and I've got 3 dots in the plane, 3 points in the plane. P, Q, and R. Okay. I need to find a vector normal to this plane. Okay. So how do I do that? What I'm going to do is I'm going to make 2 vectors out of these 3 points. What do I mean by that? Well, let's say, for example, I pick P as my starting point, and that's totally arbitrary. You could pick any of these 3 points. Well, I could make a vector from P to Q, right? This is the vector P, Q. And I could make a vector PR, okay? Now these 2 vectors are both in the plane. What do I know about the cross product of PQ and PR? That cross product, remember, the result is going to be orthogonal to both of my starting vectors. And in fact, that vector is going to be orthogonal to the entire plane. So I'm not given a normal vector, but I can find one, okay, by taking the cross product of 2 vectors in the plane. Okay, so that's what I've said here. We're to find the vector PQ and PR, both are vectors in the plane. The cross product is going to be a normal vector. All right, that's going to give us our normal vector. Once we have a normal vector, it's business as usual. You know, this vector, you know, I could pick either one of these vectors. I could pick PQ or PR. Okay, this is my normal vector n. Then I could write the equation n dot what PQ equals 0, or I could have used PR. All right, so it's fairly straightforward. Let's see a quick example. Let's say I'm told my plane contains the 3 points. Let's say it contains P is equal to 1, 3, 2, Q, negative 1, negative 4, 6, and R 2, 0, 2. How about that? Okay. So my plane contains these 3 points. Let's find the equation of the plane. So first thing I need to do is find my normal vector. Okay. Well, PQ, which is what? Negative 1 minus 1, negative 2, negative 4 minus 3, negative 7, 6 minus 2, 4. That's a vector in the plane. And PR, that's, let's see, 2 minus 1 is 1, 0 minus 3 is negative 3, 2 minus 2 is 0. That's another vector in the plane. This cross product of those two is going to be orthogonal to the plane. So let's find PQ cross PR. Remember, that's all about finding that determinant thing, right? How do we do that? We kind of make our matrix I, J, K. I like to put little, bars around my matrix because typically a matrix has these. Okay. In my second row, in my first row, I'm going to put ijk. In my second row, I put -2, -7, 4. In my third row, I put 1, -3, 0. Now I take the determinant. Okay, so I do I times, okay, I eliminate that column, that row, -7 times 0 minus -12, so times 12. Okay. I look at J, I have minus J times -2 minus 0, or -2 times 0 minus 4, so -4 plus K times 6 plus 7. So I have this vector 12i plus 4j plus 13k, which is the same as 12, 4, 13. This is my normal vector. Okay. So I've got my normal vector, and I've got plenty of, well, I've got 2 vectors. I've already found 2 vectors in my plane. These 2 vectors are in my plane, right? So I can pick either one of these. So let's pick PR, 1, -3, 0. I know n dot PR is going to be equal to 0. That's the equation of my plane, my vector equation, which I could write 12, 4, 13 dot, so 1, -3, 0 equals 0. And where's our x, y's, and z's? Okay, so this vector equation will be fine. Remember, this vector here this is not quite right. I'm missing this shouldn't be n dot PR. Instead of n dot PR, I should have n dot R minus RO, right? So RO could be this, my PR, right? So what I should have is n, so my n is 12, 4, 13 dot what? X, Y, Z minus 1, -3, 0. There. And that's equal to 0. Yep. So this would be our answer here. Again, that's in vector notation, and we could split that up to write in scalar notation as well. Which would be what? It'd be 12 times x minus 1 plus 4 y plus 3 plus 13 z minus 0 equals 0. So that would be my scalar equation of the plane. Now, if you've been trying these on your own, you might see, you might be getting different answers, but only different by like a negative sign. Okay, why is that? that could be, that's just about our choice of normal vector, okay? So in this case, so let's take a look at this example. We did PQ cross PR, right? So we did this vector cross this vector. Okay, so order matters for this cross product. So maybe if I do PQ cross PR, I get this vector here pointing upwards, right? On the other hand, if I had done PR cross PQ, I would have gotten the same vector, except it would have been pointing downwards, like everything would have opposite sign. So that would give me this vector. Okay, so if I had used this vector in my calculations, it would have been a similar equation, but sign differences would have made it look a bit different. So you could be getting different answers that are still correct. Okay, so there are, for these equations of planes, there's multiple ways to write these. Some notes when we're talking about planes. The angle, you might see questions that ask for the angle between two planes. Well, that's determined by the normal vectors. So we have two planes, each has its normal vector, right? So let's say I have this plane, okay, it's got a normal vector going this way. And then I have maybe, I'll try and draw it here. Maybe I have this other plane and they kind of intersect, right? Well, this plane has, let's say, this normal vector here. The vector between these two planes, or excuse me, the angle between these two planes is going to be the same thing as the angle between those two vectors. So remember how we find the angle between two vectors. It's all about that dot product, right? Since I know V, let's use N1, N2. Let's say I do the dot product of N1 dot N2. Okay, where like N1 is this normal vector, N2 is that normal vector. I know that dot product is magnitude of N1 times magnitude of N2 times the cosine of the angle in between them, right? Okay, and then to find the angle between them, I get cosine by itself, first of all. And then I take the cosine inverse to get theta. And that's going to give me some angle between, what, 0 and 90? Okay. So that'll be my answer there. Two planes are parallel only if their normal vectors are parallel. Okay, so that's a fact there. Last topic of this section, distances. So you might be asked, and this is an important idea. It might seem kind of arbitrary, but again, this plane, like these techniques are used a lot in applied math, like data analysis, machine learning, etc. So, for instance, a plane could represent like an approximation to some data, okay? And then, so like maybe a model of data. And then we get this real world data here, okay? So this distance here from our point to our plane could be considered like the error in our approximation, our prediction, okay? That's a really vague example, I know, but you know, it is very useful stuff. Okay, so that's, you know, just one possible application. So what are we talking about when we say distance of a point to a plane? Okay, so let's say we have this point P1 here. I'm going to draw a line directly from P1 to the plane. And what do I mean by directly? I mean that when this line hits the plane, it should hit at a 90-degree angle. If it hits at any other angle, I know that I have not taken the most efficient route, right? If I go to any other point with any other angle, this distance is going to be longer than my straight down distance, so to speak. Okay. So when we're talking about distance from a point to a plane, we always think about this vector going from my point to my plane and hitting at a 90-degree angle. So what does that remind us of? This could be a vector, right? A vector orthogonal to our plane, okay? That reminds us of our normal vector, right? Now this, we might be given a normal vector for our plane, and it might be shorter than this distance, or it might be longer than this distance. But what we know for sure is that, we can write at least part of this, this vector as my normal vector. All right, and then let's say I know some point in my plane. Let's call this p sub 0, okay? And then think about the vector that goes from p sub 0 to p1, okay? And it doesn't matter, what point in the plane I pick. All it matters is I know the coordinates of that point, okay? Now this vector is very important, okay, because if I take the projection, remember projections, if I take the projection of this vector onto n, I'm going to end up with the vector that goes from my plane to p1, okay? So think about projections again. So how do projections work? If I'm projecting, so this is a vector p0 to p1, right? Think about the projection of p0 onto p0 p1 onto n. Remember how that works. We kind of consider like a light source directly overhead the vector n. Okay. So this is like think about this as a sun, and it's shining its light straight down onto this vector p0 to p1. What kind of shadow is that going to cast on this kind of flat piece of land here? Well, let's see. The shadow would, I haven't drawn it well, but it would cast straight down, and it would cover, the shadow would cover this whole region here. It would actually be exactly this vector from the plane to P1. Okay. And the textbook gives a good illustration of this if you want to check that out. So the projection of P0, P1 onto n will give us this vector here. How does that help us? We're looking for a distance, right? A number. Okay, let's call this vector, let's call it V. That goes from the plane to P1. Okay. I know that vector is going to be the projection of P0, P1 onto n. Okay. And what is that projection? How can we write the projection? Well, remember the projection of P0, P1 onto n is given by dot product P0, P1 and n over n dot n times n. Okay. Now, this distance, the distance from my point to my plane, is just the length of the vector v. Okay, so basically what I need, this is giving me my vector v. I need to find the length of v. Now there's a shortcut that the book gives us, right? Okay, what is, So I got P0, P1 vector dot n vector over n dot n times the vector n. Okay, I'm looking for this length. Okay. Remember, n dot n remember this denominator is the same thing as magnitude of n squared. I have n. Okay, so I'm looking for the length of this vector. Well, n over n magnitude of n, this is just a unit vector, right? So it's going to have length 1. So I can forget about that, and then I would be left with P0, P1 over magnitude of n. Okay, so the length of this thing, oh, and I'm missing a dot n up here. The length of this thing, the numerical value of this, is going to be equal to my length of v. All right. So that wraps up all the material from this section. Some of it's a little strange. This distance stuff is a little weird, but we'll go over it on Tuesday in our problem session, and you'll obviously be practicing it in the homework. All right. Good luck.